let's have a look at the family tree for the quadrilaterals in all its glory. Okay. So as we know, all the quadrilaterals can be classified according to their different features. And then as we branch down, the quadrilateral becomes more and more specialised until, of course, we get to the perfect quadrilateral down the bottom, which is, of course, the square. So any property you know about a quadrilateral is also a property of any quadrilateral that branches off it. So when we say something like, well, all sides are equal in a square, it's not actually a feature of a square we're talking about, it's a feature of a rhombus. But a square branches off a rhombus, so we can say that feature. And there you go, there's another example. So a rhombus would have all the properties of any particular ones for a rhombus, but also the ones for parallelogram, trapezium, kite, and quadrilateral for that matter. Not that quadrilateral has a lot of features that are that interesting. Let's have a look at each of them. So the quadrilateral, as I was saying, doesn't have a lot of features. It's it's got 4 sides.
Oh, wow.
Yeah, there you go. Not that useful in proving things, but not only that, it's got 4 angles as well.
Whoa.
But really, a quadrilateral doesn't have any specific properties of its own. Alright, so we branch off. Let's go over to the kite. So we start specialising, and a kite, of course, is the one where the adjacent sides, so you have a pair of adjacent sides are equal. In fact, you have 2 pairs of adjacent sides being equal. We also know the diagonals in a kite are perpendicular. That one's often mistaken to be a feature of a rhombus, but it's actually a feature of a kite. And also the area formula is often quoted as the area of a rhombus, but it's actually the area formula for a kite. Half the product of the diagonals. Then over on the other side we could branch out to be a trapezium, and that's the one where you have a pair of parallel sides. And the only other thing we really know about trapezium is our area formula. Half height, which of course is the perpendicular distance between the parallel sides, and then A plus B, the sum of the parallel sides. Okay, branching off the trapezium, now we have 2 pairs of parallel sides. Other things we know, opposite sides in a parallelogram are equal. Opposite angles in a parallelogram are also equal. The diagonals in a parallelogram will bisect each other. And our parallelogram formula, base times perpendicular height. Now, if you wanted to prove any shape, all you've got to do is prove a feature. But with the parallelogram, you can actually combine 2 of them for just 1 pair of sides. So if you've got 1 pair of sides and you know they're both parallel and equal, then that's enough to say the shape's a parallelogram. Okay, so we've got the kite, we've got the parallelogram. Parallelogram now branches down to the rectangle, and that's when we make a vertex angle equal to 90 degrees. Remember, you only really have to show one angle is 90 degrees because of the parallel sides. You could easily say co-interior angles, etc., etc. So if you know it's a parallelogram, you don't have to show all the angles are 90, just one. And now the diagonals become equal. The diagonals are equal. And length times breadth is our formula for the rectangle. A rhombus, which is both a parallelogram and a kite. So it has the features of both the parallelogram and the kite, but it has an added one, which is the diagonals bisect the vertex. And of course that then branches down to the square, which by itself doesn't really have any properties, it's just that it has all the properties of all the shapes. And if you wanted an area formula, amazingly, it's the side squared, hence the name of the shape, square. Okay, so 8D, E and F are all different ones on parallelograms and rectangles and, well, our quadrilateral exercises.